Power capacitor installation at a power plant can have several effects, depending on its location and the system's initial conditions. Let's consider the initial scenario where a capacitor is installed on a distribution line that is 20 kilometers from the power plant, serving a 2000 kilovolt ampere load with an initial power factor of 0.7 lagging. Firstly, when the capacitor is installed on the distribution line, it reduces the current flow in the distribution line. Secondly, this leads to lower active losses, also known as I2R losses, in the distribution line. Thirdly, installing the capacitor improves voltage regulation at the load end because the capacitor provides reactive power support locally, reducing the voltage drop along the line. If the capacitor is then shifted to the generator, firstly, it reduces the reactive power demand from the generator. Secondly, this improves the power factor at the generator terminals, bringing it closer to unity. Thirdly, placing the capacitor near the generator reduces the voltage drop in the generator windings and the transmission line because the reactive power is supplied closer to the source. Overall, the effects of installing and shifting the capacitor result in, firstly, improved power factor throughout the system. Secondly, this reduces active losses and voltage drop in the system. Thirdly, increased system efficiency is achieved because less power is wasted in the form of heat due to lower current and improved power factor. Now let's examine the effect of a leading power factor in the system. We'll consider an initial scenario with a power factor of 0.7 lagging, which is typical for many inductive loads. When the power factor becomes 0.7 leading, meaning the current leads the voltage by a significant angle, the following effects occur. Firstly, the inductive load will now appear as a capacitive load to the source. This means the system is overcompensated with capacitance. Secondly, inductive line losses are reduced while capacitive line losses increase. This is because the reactive current flow changes direction and interacts differently with the line impedance. Thirdly, voltage regulation at the load end may become excessive, leading to overvoltage problems. This is because the capacitive load tends to increase the voltage, and if not properly controlled, can cause equipment damage. Fourthly, over-excitation of the generator may be required to maintain the leading power factor, which can reduce generator efficiency and stability. This happens because the generator has to work harder to counteract the excessive capacitive reactance. Overall, while a leading power factor can improve the power factor at the load end, it also leads to increased capacitive losses in the distribution line and potential overvoltage and generator over-excitation issues. It is crucial to maintain a power factor close to unity without overcompensating, as both lagging and leading power factors have their drawbacks. The specific effects and optimal capacitor placement will depend on the system's parameters and load characteristics. Power factor correction is a crucial aspect of electrical power systems. It aims to improve the efficiency and stability of the system by minimizing the reactive power flow. A power factor close to unity is desirable because it indicates that the electrical power is being used effectively with minimal reactive power. Reactive power does not contribute to the actual work done by the load but circulates in the system, increasing current flow and losses. Capacitors are commonly used for power factor correction because they provide reactive power that counteracts the effect of inductive loads, which are common in industrial and commercial settings. When a capacitor is installed in a power system, it supplies reactive power locally, reducing the amount of reactive power that needs to be supplied by the source, typically a generator or the grid. This has several benefits, including firstly, reduced current flow. By supplying reactive power locally, the capacitor reduces the amount of current flowing through the transmission and distribution lines. This is because the reactive current component is reduced. Secondly, lower losses. The losses in the power lines are proportional to the square of the current, known as I2R losses. By reducing the current, the losses are also reduced, improving the overall efficiency of the system. Thirdly, improved voltage regulation. The voltage at the load end tends to drop due to the impedance of the transmission lines. By supplying reactive power, the capacitor helps to maintain the voltage at the desired level, improving the performance of the equipment connected to the load. However, it is important to note that overcorrection can lead to a leading power factor, which can also have negative effects, as we discussed earlier. The ideal power factor is close to unity, typically between 0.95 and 1.0. When a capacitor is shifted closer to the generator, the benefits become more pronounced. This is because the reactive power is supplied even closer to the source, further reducing the current flow and losses in the system. The location of the capacitor also affects the voltage profile in the system. By placing the capacitor closer to the generator, the voltage drop in the generator windings and the transmission line is reduced, leading to a more stable and efficient operation. In addition to capacitors, other methods can be used for power factor correction, such as synchronous condensers and static VAR compensators. Synchronous condensers are synchronous motors that are operated without a mechanical load. They can be used to supply or absorb reactive power, depending on their excitation level. Static VAR compensators are electronic devices that can provide dynamic reactive power compensation, responding quickly to changes in the load. The choice of method depends on the specific requirements of the system, such as the size of the load, the voltage level, and the desired level of power factor correction. Power factor correction is an important aspect of power system design and operation. It can improve the efficiency, stability, and reliability of the system, reducing costs and improving the overall performance. Careful consideration should be given to the location, size, and type of compensation equipment to ensure that the desired level of power factor correction is achieved without causing any negative effects. Maintaining a power factor close to unity is essential for efficient and reliable operation of electrical power systems. Power factor is the ratio of real power kilowatts to apparent power kilovolts amperes in an electrical circuit. It is a dimensionless number between 0 and 1. A power factor of 1 indicates that the voltage and current are in phase and all the power supplied is being used to do work. A power factor less than 1 indicates that the voltage and current are out of phase and some of the power is being wasted as reactive power. Inductive loads, such as motors and transformers, cause the current to lag the voltage, resulting in a lagging power factor. Capacitive loads, such as capacitors, cause the current to lead the voltage, resulting in a leading power factor. In most industrial and commercial facilities, inductive loads are more common, so the power factor tends to be lagging. A lagging power factor can have several negative effects on the power system, including firstly, increased current flow. For a given amount of real power, a lower power factor means a higher apparent power, which translates to higher current flow in the conductors. Secondly, higher losses. The losses in the power lines are proportional to the square of the current. Higher current means higher losses, which wastes energy and increases costs. Thirdly, reduced capacity. The higher current also reduces the capacity of the transformers and conductors, limiting the amount of power that can be delivered to the load. Fourthly, voltage drop. The higher current causes a larger voltage drop in the conductors, which can affect the performance of the equipment connected to the load. Fifthly, increased costs. Utility companies often charge penalties for low power factors, which can significantly increase the electricity bill. Power factor correction aims to improve the power factor by reducing the amount of reactive power in the system. This is typically done by installing capacitors, which supply reactive power that counteracts the effect of the inductive loads. By improving the power factor, the current flow is reduced, which in turn reduces the losses, increases the capacity, improves the voltage regulation, and reduces the costs. The size of the capacitor required for power factor correction depends on the amount of reactive power that needs to be compensated. This can be determined by measuring the power factor and the real power consumption of the load. The capacitor is typically installed close to the load to minimize the current flow in the conductors. In some cases, it may be necessary to install multiple capacitors at different locations in the system to achieve the desired level of power factor correction. It is important to note that overcorrection can lead to a leading power factor, which can also have negative effects. A leading power factor can cause overvoltage problems, especially in lightly loaded systems. It can also cause instability in the generator and other equipment. Therefore, it is important to carefully size the capacitor and monitor the power factor to ensure that it is maintained within the desired range. Power factor correction is an essential aspect of power system design and operation. It can improve the efficiency, reliability, and cost-effectiveness of the system. By understanding the principles of power factor correction and implementing appropriate measures, it is possible to optimize the performance of the power system and reduce the overall energy consumption. The effects of installing a power capacitor can be further understood by considering the specific parameters of the system. The size of the capacitor should be chosen to provide the appropriate amount of reactive power compensation without overcorrecting the power factor. Overcorrection can lead to a leading power factor, which can cause voltage instability and other problems. The location of the capacitor is also important. It should be installed as close as possible to the load that is causing the lagging power factor. This will minimize the amount of current flowing through the conductors and reduce losses. In some cases, it may be necessary to install multiple capacitors at different locations in the system to achieve the desired level of power factor correction. The type of capacitor used is also important. There are two main types of capacitors used for power factor correction: firstly, shunt capacitors, and secondly, series capacitors. Shunt capacitors are connected in parallel with the load and provide reactive power compensation. Series capacitors are connected in series with the load and reduce the impedance of the line. Shunt capacitors are more commonly used for power factor correction because they are less expensive and easier to install. Series capacitors are typically used in long transmission lines to improve voltage stability and increase the power transfer capacity. The installation of a power capacitor should be done by a qualified electrician. The capacitor should be properly sized, located, and connected to ensure safe and reliable operation. The system should be monitored after the installation to verify that the power factor has been improved and that there are no adverse effects. Power factor correction is a complex topic, and it is important to consult with a qualified engineer to determine the best solution for a particular application. By understanding the principles of power factor correction and implementing appropriate measures, it is possible to improve the efficiency, reliability, and cost-effectiveness of electrical power systems.